today I'll be talking about F10, a fault-tolerant engineered network. This is work that I did with Dan Halperin, Arvind Krishnamurthy, and Tom Anderson at the University of Washington. And so, as data centers have scaled, bisection bandwidth and cost concerns have led to the use of commodity switches and multiple paths between those switches. These so-called next-generation data center proposals, like FatTrees and VL2, are based on folded class topologies like the one shown here. These topologies are arranged as multi-rooted trees, where each layer is grouped into different subtrees. In this image, for example, the top-level root switches are connected to 4 such subtrees. These networks are able to provide low-cost, high bisection bandwidth, and resilience to failures. For example, if we look at how failures are handled in Portland, a paper that showed how to implement FatTrees with current hardware, failures are detected using keep alive messages or heartbeats. And upon detection, a centralized controller can then go and install updated routes into the affected switches. It's able to do this. It's able to route around the failure because path redundancy exists in the topology. And so Portland is able to solve a bunch of problems in this space. And while it seems like this might be a reasonable solution to provide resiliency in data centers, it's the case that there are a bunch of unsolved problems. The first is that detection is slow. So all of that path diversity that I mentioned in the previous slide was obtained at low cost by using commodity switches. These types of switches tend to fail pretty often and also sometimes fail in strange ways. For example, they could experience gray or partial failures where maybe they're delivering half of all traffic. And that may be enough to send the occasional heartbeat, but probably isn't enough for good application performance. And the second problem here is that even after we've detected the failure, restoration of connectivity is really slow. We aren't able to actually recover immediately or at the point of the failure. And this goes beyond Portland's offloading of failure recovery to a centralized controller. As I'll show later in this talk, the topology itself doesn't allow us to do local recovery. And finally, even after the recovery is complete, the failures can still come to bite us. Long-term failures can actually leave the tree in an unbalanced configuration. What I mean by that is that the loss of switches and paths removes the nice symmetry that's in these topologies, and with it, their load balancing properties. And so our approach in F10 is to co-design the topology, routing protocols, and failure detector to improve failover in all 3 of the phases I just mentioned, namely detection, restoration of connectivity, and post-restoration. In particular, we introduce a novel topology that enables immediate recovery at the point of the failure. We also introduce a cascading set of protocols that allows us to both recover immediately and restore global load balancing. And finally, we introduce a fine-grained failure detector that gives us fast and accurate failure detection. We do all of this with the same number of switches and links as a traditional FatTree or other folded class topology. And so in the rest of this talk, I'll go into each of these 3 components in a little more detail, starting with our novel topology, which we call the AB FatTree, followed by our cascaded set of routing protocols, and finally our failure detector. But first, why is recovery slow in a FatTree? Well, this diagram shows a fully provisioned FatTree where the boxes represent switches and the lines represent links between those switches. In this diagram, each switch has 4 ports for space purposes, and it's drawn in the way of the SIGCOMM 2008 paper, which is to say that subroutes are connected to consecutive routes. And so when this source on the very right wants to send to this destination on the very left, what it does is it sends a packet upwards until it reaches a route with a direct path to the destination. And actually, it's the case that at each of these levels, we could have taken a different path. And so there's actually a fair amount of path diversity that's inherent to this topology. And so when a failure occurs on the upward half of this path, we can exploit this property to immediately restore connectivity at the point of the failure. However, if we go back to this original path and we take a look at a failure on the downward half of the path, recovery isn't so straightforward. It's actually the case that the node immediately prior to the failure doesn't have any direct alternatives around the failure. And actually, if we trace backwards along this path, we'll see that most of these nodes actually don't have alternatives. Only the source switch can actually route around the failure. And in some sense, there's this point of no return on this path that's really troublesome. And if we look at all paths that pass through the failure on the way to the destination, we'll see that, at least in this example, the switches that have alternatives, the ones that actually need to be involved in recovery, those switches are all the way on the other side of the network. The problem with this topology is actually its symmetry. Each node is connected to the same set of parents as their siblings, and the exact same set of grandparents as their cousins, and so on and so forth. What we propose is to break this symmetry slightly in order to allow for immediate recovery at the point of the failure. And to this end, we introduce a type A subtree that's connected in exactly the same way as a classic subtree, which is to say that nodes are connected to consecutive parents. In this example, node X is connected to switches 1 and 2, whereas Y is connected to 3 and 4. To this, we add a type B subtree that's connected in a strided fashion. So here, instead of, so X is connected to 1 and 3 instead of being connected to 1 and 2, and Y is connected to 2 and 4 as opposed to 3 and 4. And it's important to note that clearly, if you build a tree out of only type A subtrees, it's exactly the same as a traditional fat tree. But it's also the case that if you build a tree out of only type B subtrees, it's also identical to a traditional fat tree. It's just drawn in a little bit of a different way. We propose an AB fat tree instead, where half of the subtrees are of type A and half are of type B. Because of this break in symmetry, it's now the case that siblings aren't connected to the same set of parents anymore. And so if we go back to this example we had before, where a source is sending to a destination, and there's a failure on the downward half of the path, we see that there are a lot more alternatives in this topology, and that they're much closer to the point of failure. In fact, instead of needing to inform switches all the way on the other side of the network, this topology actually guarantees that every switch is at most one hop away from a node with an alternative. That now gives us the ability to recover immediately at the point of failure. And it's in this context that we implement our failover protocols. We use 3 mechanisms that are in slightly different timescales. A local rerouting mechanism that immediately restores connectivity at the point of failure. A pushback notification scheme that restores shortest paths on the order of a few milliseconds. And finally, a centralized controller that globally re-optimizes traffic every few seconds. The first of these is local rerouting, which uses this property that we're most one hop away from a node with an alternative. Note that for illustrative purposes, I've changed this diagram slightly to be an ABA fat tree. But in this example, we still have this switch, U in this case, that wishes to send to the destination through a failed switch. To do this, it simply routes to a sibling in an opposite type subtree. In this case, that sibling is in a type B subtree. And in this way, we can get around the failure really easily. And it's actually the case that this scheme generalizes to multiple failures as well. For example, if we had another failure right here, we could avoid these two concurrent failures by simply routing to another parent. In fact, our local rerouting scheme is guaranteed to find a route up until you have enough concurrent failures to disconnect the network. I won't get into the details of that here, but you can refer to the paper if you're interested. But so this is great and allows us to instantaneously recover from failures, but it comes at the cost of a slight bit of path dilation and also a bit of increased load. To fix that, we actually take advantage of the increased number of alternate paths closer to the failure and try to use them instead of the longer rerouted paths. Note that we'll consider a link failure in this case for simplicity. But in this protocol, the detecting switch, again U, broadcasts out a notification to each of its neighbors. As soon as this notification reaches a switch with an alternative route, it terminates. Otherwise, for the other two switches that don't have alternative routes, they continue to broadcast out the notification. So in this example, 3 nodes need to be notified of this failure. And as soon as they are notified, they can stop sending along those failed paths and use their alternatives. So this provides us a bit of local load balancing, but doesn't completely handle the loss in symmetry introduced by the failure. In fact, it's sometimes the case that the entire network needs to be rebalanced, since flows that aren't even on the failed path may need to move in order to make room for flows that are. This global rebalancing of flows is handled by our centralized controller, which borrows ideas from existing work like Hedera and MicroTE. How it works is that the controller gathers traffic matrices from top-of-rack switches or servers, and then places long-lived flows based on their size. Shorter flows that are too transient to take advantage of this periodic rescheduling are placed with a form of weighted ECMP, which basically means that they're placed on randomly chosen paths based on the residual capacity on that path. And so after we finish this, after this phase, we've restored the system to the best state we can given the failure conditions. And to set this chain of events into motion, we use a fine-grained failure detector. So today's failure detectors are generally based on keep alive or heartbeat messages, partly because in traditional systems, the detector is actually separated from the failure. These heartbeats are relatively slow, intentionally slow, because congestion and grave failures can potentially cause false positives. It's also the case that we'd rather not waste too many network resources with constant pinging. And so F10's failure detector instead looks at the link itself. So what happens is that each switch will continually send traffic to neighbors even while idle. And in that way, switches can simply monitor incoming bit transitions and number of correct packets in order to detect when when their neighbor goes down. As soon as we detect a failure, we reroute the very next packet and then stop sending so that failure detection is bidirectional. We can do this, we can be very aggressive here because rerouting in our system is cheap. It's the case that, at least in local rerouting, we can both initiate and tear down reroutes at the detector unilaterally. And it's also the case that none of our routing protocols can result in routing loops. And so those 3 components are what make up what we call F10. To evaluate our system, we asked a few questions. In this talk, I'll go over 3 of these questions. There are more in the paper if you're interested in that. The first was, can F10 do rerouting quickly? Can our topology changes and local rerouting protocol actually recover from failures immediately. The second question we asked was whether or not F10 can avoid the congestion loss that results from failures. And finally, we asked how much do these things actually affect end-user application performance. We tried to answer these questions using both a small testbed and a packet-level simulator. The testbed used a click implementation on top of Emulab, but since our prototype was bandwidth limited by both Emulab and click, we used smaller packets to compensate for that. We also built a packet-level simulator that was intended to test medium to large deployments of F10. So this simulator emulated 24-port 10 gigabit Ethernet switches, 3 levels of these in a fully provisioned FatTree. And we used a realistic traffic and failure model published in recent measurement studies. We then validated the simulator using our testbed implementation. And so to show that F10 can reroute quickly, we ran a Linux TCP stream over our Emulab testbed and induced a failure on the downward half of the path. When we looked at the congestion window size of the sender, we then looked at the congestion window size of the sender in order to get a sense of how quickly F10 recovers from failures and what that actually means for an end host that's using a failed path. This graph shows congestion window size versus time, with and without a failure. You'll notice that when we induced the failure at around 15 seconds or 15,000 milliseconds, we lost a few packets, but F10 was actually able to recover in under a millisecond, which is much less time than a TCP timeout. So if we didn't have F10 in this case, packets would stop being delivered, and we would induce a TCP timeout where we have to go back down to 0 and do this whole mess on the left. To show that F10 can avoid congestion loss, we used our simulator to compare F10 in Portland under the realistic traffic and failure conditions that I described previously. We aggregated traces into time intervals of about half a millisecond and looked at the congestion loss, or fraction of packets dropped, for each source-destination pair. This graph shows a CDF of that congestion loss, and you'll notice that in 70% of the intervals, F10 actually didn't experience any loss at all. It's also the case that Portland has 7.6 times the congestion loss of F10 under these conditions. This congestion loss manifests itself in end-user performance. We ran a commonly used MapReduce trace over the previous setup and monitored end-to-end performance of a complete MapReduce drop. This graph shows a CDF of the speedup of F10 versus Portland, or job completion time of Portland over F10. And we observed that the median speedup in this case is around 1.3 times. If there was no benefit from F10, this would essentially be a line at x equals 1. And the reason why F10 is so much better is that MapReduce is an example of a common class of data center applications that are affected by the slowest node, which means that even if only a small fraction of the flows are affected by a failure, they end up slowing down the entire MapReduce job. And so, in conclusion, I presented F10, which is a co-design of topology, routing protocols, and failure detector, where each of these mechanisms support and improve each other. And in particular, I presented an A/B FatTree that allows for local recovery and can increase path diversity closer to the failure. I also introduced a set of cascaded routing protocols that can restore congestion-free operation. And finally, I showed that F10 gives significant benefit to application performance on typical workloads and failure conditions. Thanks.
Hi, really enjoyed your talk. Brad Karp, UCL. I just wanted to ask, I think in your paper you say that in the situation where you don't have control over the end host operating system and can't do multipath, you might need a network level solution like F10. I sort of wanted to flip that around and ask, have you thought about doing a comparison where you actually would have the option of using, say, MPTCP? How would the F10 solution compare in the various performance metrics that you've talked about versus a solution like MPTCP?
Yeah, so we haven't done that evaluation yet, but as you said in the paper, we're targeting a slightly different case where you don't necessarily, or you aren't necessarily able to affect end host VMs. You want them to be able to use their own VM, their own custom VMs.
Would you care to speculate about what you expect?
I hesitate to speculate too much because I might say something wrong. But I think that even with multipath TCP, you're still going to get a slight performance degradation in that you'll lose one of your paths. So depending on how many paths you have, you'll lose some fraction of that, which potentially could be worse than F10.
Thanks.
Vincent, Princeton. So I had a question about, so I realize you're adding more links as you get closer and closer to the sources to give you that redundancy and to make it easier to fail over. I was just wondering if you used like a VL2 type of topology where, you know, the aggregation and core switches were fully connected, would you get a lot of the benefits that F10 is suggesting?
So
you only have to go back basically up to the core, and then you usually have a route back down to the node that may have
right. So I mean, I was under the impression that VL2 also uses a Coloss topology, but I'll answer the question for more traditional data center topologies where you do have that sort of all-to-all connectivity at certain layers. And so even for those cases, you're going to get that. You're going to get maybe 50% benefit over traditional FatTrees. But it's the case that, like, why wouldn't you want to further optimize that using F10's AB FatTree?
Thanks.
Hi, Kyriakos, University of Southern California. I was just wondering, so one of the nice properties of having symmetry is that load balancing happens kind of naturally, in the sense that if you have a good hash function and some workload that is not too skewed, presumably it will just be pretty uniformly distributed. And I was wondering if you miss out on some properties, something like that, by breaking the symmetry.
Right, so that's a good question. It's actually the case that we don't change that. So the way load balancing is done is that you split over the multiple upward paths, right? And in our case, our topology, you can do the same thing and get the exact same benefits. The proof of that is fairly involved.
So you wouldn't need some kind of manual load balancing scheme that reflects the topology?
No, you wouldn't.
You wouldn't need to change.
Yeah.
Thanks.
Hi, Naveen Jain, Microsoft Research, Redmond. I really like the fact that some of your design is driven by real failure data, so very cool. I have two questions. First, in your pushback notification scheme, whenever a link fails, I see the effect getting amplified in terms of broadcast notifications in the rest of the network, right? So imagine a scenario where you have a link flap, which occurs more often than you think, right? Do you think you're essentially now reacting too fast, you're actually causing more problems?
So there's two parts of that question. So the question was, or let me.
The question is, reacting too quickly to links going up and down, are you actually now inflating the impact?
So I think the first part of that question is the efficiency of the pushback broadcast scheme. We don't have a graph of that in the paper, but there's a tech report that shows that the actual number of messages we broadcast is actually not that high per failure. The other thing here is that even if we have link flapping, we actually do exponential backoff just like in normal, or just like in classical networks, in order to limit that effect.
Okay, and my second question is for your global scheduler. You're making an implicit assumption that your TMs, your traffic matrices, are stable. How stable are they?
So Yes, but I think previous work in Hedera and MicroT showed that at least there exists elephant flows, part of that long tail, where you can actually predict those and you can actually place them. There are also a bunch of flows that are unpredictable. And it varies based on application workload. But I think there's evidence that a lot of realistic things could benefit from this. It's also the case that even if things are unpredictable and balanced, our centralized scheduler actually still gives a benefit in the fact that it does it changes the weighted ECMP values across the entire network as opposed to pushback, which doesn't.
I guess my question was literally that you're.
In the interest of time, I think if we can maybe.
Okay,
Okay, sure,
we
let's
can
take it
take this offline.
Yeah,
Sorry.
sure. Well, let's thank Vincent once again.